Hello everybody. First of all, I would like to introduce myself. I'm Professor Francois Garde. I am involved in this ABC21 project. I am a professor and teach at the Université of Rénion, which is a small island located in the Indian Ocean. I will present the case studies that we have identified in this European project. So what is ABC21? ABC21 is the acronym for Africa and Europe Bioclimatic Buildings for 21st Century. The aims of this project is to identify and document African and European bioclimatic designs with the use of local materials. The idea is to suggest methods to promote sustainable energy efficient buildings, taking into account affordability and replicability of those buildings. So in terms of case studies, we have identified 24 buildings in two phases. Phase 1 has been completed and phase 2 is ongoing, and in each phase we have identified perfect buildings, bioclimatic buildings in the south of Europe and in Africa, including Réunion Island. On phase 2, we plan to have a feedback to monitor some buildings and to have a post-occupancy evaluation about some of these buildings. All those buildings are bioclimatic buildings, and these buildings use natural cross ventilation. So in terms of definition, there are three cases of ventilation. First of all, ventilation can be used for hygienic purposes. That means that we need, in this case, just one air change rate per hour, just for hygienic reasons. The second case where we can use ventilation, natural ventilation, is to evacuate the internal loads. In that case, the level of air change rate per hour is 10. And the third case, it is the most important case, it is where we really need the use of natural cross ventilation to have a better thermal comfort, is to have an air change rate of 60 air change rate per hour. In that case, we can reduce the temperature that we feel by 4 degrees. In this slide, you can see the comfort zone, it's in blue, and on the y-axis you have the temperature, and the x-axis you have the air velocity. The blue dot that you can see on this slide represents the comfort zone for a temperature of 30 degrees and 1 meter per second. That means that if we are able to create an air velocity of 1 meter per second in the indoor spaces, we can feel comfortable with air temperature around 30 degrees, which is really high, but we can feel very comfortable. If there is no wind, the role of ceiling fan is really important, because ceiling fan can create the air velocity that we need to create the thermal comfort. So the ceiling fans, if installed in a space, can reduce the field temperature. You can feel a temperature 4 degrees below the air temperature. It reduces the period of air conditioning, for instance, and if the air temperature is below 30 degrees. And ceiling fans can be combined with air conditioning. They allow to have a higher set temperature. For instance, you can set a temperature at 28 degrees with air conditioning in ceiling fans, and you can feel comfortable. And if you use ceiling fan in those cases, you can reduce the energy consumption by 30 to 95%, which is a huge amount of energy savings. Here you have in this slide some 6 of the case studies that we have identified in the phase 1. You have buildings in Senegal, Maison des Énergies. You have a building in Kenya, an office building, the United Nations office building. You have 3 buildings in Morocco and 1 building in Sudan. It's the Salam Cardiac Surgery Center, just to show you some of the case studies we have identified in phase 1. In phase 2, we are at the moment involved in the selection on the case studies. This is a social housing building project located in Rénion. The name of this building project is Forest Malaka. It's a 6 stories building. The climate is humid tropical, and it's the buildings are very thin and narrow, just to encourage the use of natural cross ventilation. Another case studies that we have identified is a high school building located in Burkina Faso. The architects are Kere Architecture, and in terms of passive solution, all the classrooms are naturally cross-ventilated. They have good solar protection. They use local materials like laterite stone and eucalyptus wood wraps. I would like now to have a special focus on one case study. It's the building of the Faculty of Engineering called Eziroi. It's located in Indian Ocean in the island of La Réunion. This building has been designed by and for natural ventilation. The shape of the building, it's like a C, and the C faces the trade winds. So you can see the windrows on the right hand side of the slide, and the shape of the building has been influenced by the trade winds. Inside the sea, because of the trade winds, we create a high pressure. The wind creates a high pressure zone, and on the other facade of the building you have a low pressure, and it's the difference of pressure that creates natural ventilation inside the classrooms and inside the spaces. In terms of main features of the building, in terms of passive design solution, most of the spaces are naturally cross-ventilated, and every spaces have 25% of porosity. Porosity means the percentage of holes, of openings for each spaces. All the buildings in this project are very narrow, 6 meters maximum. We have large glass louvers. All the facades are light facades, and they use a material called dampalon. And we have all the solar shadings are detached from the main facades, 1 meter from the facades. This is to have a better natural lighting. In terms of energy efficient solutions, we use LEDs in all spaces. We have highly efficient ceiling fans in all spaces, even those who have air conditioning. And we use an air conditioning system with a very high coefficient of performance. These buildings has been completed 2 years ago, so we have now data of energy consumption. So the natural ventilated spaces, we have an energy consumption of 20 kilowatt hour of electricity per square meter per year, which is 5 times less than a standard building, standard academic buildings in La Réunion. And the air conditioned spaces, they have energy consumption of 80 kilowatt hour of electricity per square meter per year, which is, let's say 20% less than a standard building, a standard academic building. The pictures you can see are the solar canvas in the middle of the sea of this building, and you have a typical classroom. The picture of the right hand side at the bottom of the slide is a typical classroom. This building has been, all the design solutions have been validated with wind tunnel tests. So you have a model of the building, and the model has been tested at the Eiffel laboratory, which is located in Paris. This allows us, and this allows the design team to validate the principle of natural ventilation. We could measure air velocities inside some of the spaces, pressure of the facades. And it was very interesting, and we could validate the solutions made by the architect. Here you have two pictures of a typical office. So the office are, the size of the office are 6 meters deep by 3 meters wide. In terms of passive design, all the desks are parallel to the airflow. We use vertical louvers to adjust natural ventilation. Every users have a seat with a mesh so that we can increase the, let's say, the air exchanges of the back. And the door, all the doors have magnetic door stoppers. And in terms of energy efficient solutions, every offices they have LEDs. We have one ceiling fan per user, and we don't have any kind of air conditioning systems in all the offices. Here you have a typical classroom. The size are 6 meters by 7 meters. In those classrooms, we can host 40 students. The passive design principles are the same. We use vertical louvers. We have light facades. And in terms of energy efficient solutions, we have one ceiling fan for 10 square meters. We have no air conditioning systems, and we use LEDs. Here you have pictures of other spaces. We have an open space, which is also naturally cross-ventilated with no air conditioning. And we have outdoor spaces covered by solar canvas. The cafeteria of the staff. You have the picture of the cafeteria of the staff, and you can see there's a big fan above the terrace in case of hot and uncomfortable days. So if this is the end of my presentation. In terms of conclusion, what solution set I used for the case studies that we have identified in this European project. First of all, what is important, we need to have vegetation and trees around the building to create a comfortable environment around the building. All the buildings are usually narrow. The thickness of those buildings are 6 to 7 meters deep, and in terms of stories, 5 to 6 stories maximum. We use glass louvers and detached solar shading devices. Those buildings can use air conditioning with ceiling fan, what I call the mixed mode buildings. That means that you can use natural cross ventilation with ceiling fan. This is an option. You can use air conditioning with ceiling fan, and in every cases, ceiling fans must be installed systematically. I thank you for your attention.